Yeah, thank you, Professor.
Okay.
So, guys, good afternoon and good morning from India. I'm going to handle word embeddings. As you've seen here, word embeddings is the session which I'm going to handle. So, along with this week, I will be requiring one more week also to cover the complete things in word embedding. So before jumping into the word embeddings, I'll be handling uh, why the word embeddings are actually required and how we actually moved towards word embeddings. So to cover it up, I have created a theoretical slides. Few slides are there. The presentation going to be dry, but just try to stay with me. It will give a lot of information. And in the Slack channel, I already shared the link for this uh, collab tutorial, which we are going to do hands-on. So which you can directly open in the collab and we can actually practice the same as well. So before getting into the hands-on, I'll be starting a few information about the text representation and what are the things we are going to cover it up. And please interrupt me whenever you have any queries. Okay, or if I'm going a little bit faster also, please let me know. So, the first thing is why we need the text representation and why we're actually doing this word embeddings. Okay. So, unlike the unstructured data speech or the image, the text are actually symbolic in nature. So, if you take the image, when we actually calculate the pixel, the direct numbers itself will convey the context of the image. Like if you take the speech, the amplitude and the frequency are directly produces the numbers which can actually represent the speech. But coming to the text, when we want to actually represent them to feed it to the computers to do some task, it has to be converted into symbolic form and represent them in the numerical format. So that representation of text into the numerical format only we calling embeddings. So getting inside the text representation, what are the types of representation that we have, which is commonly we used in an academic research as well as industry applications. So we have two type of primary representation. One is vector representation, which is called embeddings. Another is actually knowledge representation. So when we do the vector representation, we aims to represent the text in the sequence of numbers like arrays or in the terms of matrices as in a number. And coming to the knowledge representation, it's a kind of a graph representation. So which we actually the concepts of the text will be mapped to the graph. That graph can be used for doing some kind of interpretation and analyzation and etc. Okay. So to inside the vector representation, we have primarily two representation method. One is actually frequency representation. Another is semantic representation. Frequency representation is nothing but just counting the words in numbers. Okay. Coming to the semantic representation would be trying to convey the context of the text. I having a upcoming slides which is explaining in detail, but this is the overall semantic what we are going to cover it up. Then knowledge representation, as we know, it's actually representing text as a graph. Like for example, if you take our Wikipedia, the Wikipedia is entirely built on DBpedia. So the DBpedia is nothing but it's a connection of words and their relations to which formulate as a graph. That graph is actually produced in terms of Wikipedia text. Okay. So in order to create that entities, that is words and its relations, we might have to do part of speech tagging, entity recognition, or parsing kind of activities. So I'm starting with the vector representation, how we are actually doing a different types of methods which represents the text into the number sequence of number. So I'm just using my one of my examples which I actually created in my previous studies. So here the word SEN is my department, Computational of Engineering and Networking in Masters when I did. And Amrita is the institute which I studied. and CBE is nothing but Coimbatore. So what it says like that we have three sentences. We are in Sen. Sen is in Amrita. Amrita is in Coimbatore. Okay. So what we are going to do is like, in order to process this, first we have to like convert them into matrices. So to do the matrices, is fundamental one method is actually term documents matrix. So what we are going to do is like we collect the unique words in this all three sentences. Like as you see, Amrita, R, Sen, CB, in, is, we. As in columns, these are called terms. And in the rows, we have the sentences like sentence 1, sentence 2, sentence 3. And next, what we're going to do is like we're just going to count in the sentence 1 how many times the word Amrita present. So if you take sentence 1, there is no Amrita, so we're putting 0. R is there, 1. Sen is there, 1. CB is not there, 0. In is there, 1. Is not there, 0. V is there, 1. So like that, we can actually like fill it for other two sentences also. So here in the frequency representation, given the text, we are actually like counting the frequency of the number of frequency means number of terms. So number of terms the word appear in that sentences. Okay. So this is frequency representation. The semantic representation means like mapping a text to a sequence of numbers which reflects the context. Okay. So you can just like consider the scenario. Your friends calling you, okay, and they're actually like describing the match they saw. Okay, so they're actually explaining some Tanio scored a beautiful goal. So when you just like close your eyes and just like read, like hear this sentence, you will get a visual perspective inside your brain, right? That is basically a semantic or the context. So this context, how we are going to represent as a sequence of number. So those methods comes under the semantic representation. So the how it actually like helps is if you just like take a two words, politics and economics, okay? So when you just like blindly read these two terms, you might actually like feels though they don't have like direct relations. But if you actually like relate these words, politics and economics, with the discussion in the parliaments, like you will get the election, Democrat, Speaker of the House, budget, tax, inflation. So when it says like that economics is actually discussed in some political debate or political platform uh, about that scenario. So like the politics and economics has the somewhat like semantic relations. And these are the other terms which connects these two domains or like specific words. So how to capture that semantics is some methods are there to do that. So those methods comes under semantic representation. Knowledge representation, as I mentioned earlier, the DBpedia is actually like quite good example for it. So if you actually like see that, the each colors actually like represent the entities belongs to a specific domain. Okay, so here the pink is actually refers to the life sciences, and yellow is actually like related to the geographic, like US census, geonames, US species, etc., place names, and etc. Okay, and the green are actually like publications like DBLP, Semantic Scholar, bibliography, RDF book templates, etc. Okay, so when we actually like put all these entities in as a node and their relations or the concept in the edges, this formulate a graph. So this basically a knowledge representation text represented using a graph, that is knowledge representation. Okay, so in order to do that, we would be like doing wants to find out the entities through the part of speech tagging or the named entity recognition. Okay, so if you take this simple example, my name is Bharathi Ganesh and I live in India. So if you take Bharathi Ganesh is the person and India is the location, the relation is actually like live in. So this Bharathi Ganesh has become one entity, that is one node. India has become another node, and the concept which is actually connecting as edge is actually like live. So the person lives in a country. So that is the concept, knowledge graphs, how we actually do it. And further, other representation methods, how we can actually derive the relations are through the constituency passing or the dependency passing. So like in the earlier sessions, we actually introduced with the dependency passing, how the words and their relations are actually connected with each other. So these are actually used to derive the relations between the phrases and the words. Now, before getting inside the next with the vector representation in the detail, I just want to actually explain about what are the fundamental properties a good algorithm or the representation method should reflect, so that it will actually gives a complete representation to the text. Okay, so if you just take a word, okay, like a sentence, Tom ate an apple. Okay, so the word itself has a meaning. Okay, and how the word is actually formulated will have the meaning. Suppose if we take the word play and the played. Okay, so the inflectional forms actually formulated along with the play to convey the past tense. They already actually played. So how the word is actually formulated, and the word itself is actually contain the meaning, and the word order, how they actually appears in a sentence, and how their structure is actually constructed. So all this together, if any representation method is actually includes all this property, so that will actually act as a good representation method. So we are going to see a one by one each representation method, and we are just going to validate that whether each representation method will actually satisfies those these properties. Okay. And this graphs is actually the curves of NLP, which is familiar one in the NLP domain, which actually explains the growth of the NLP domain. So initially, till 2000, around 2000, we will be mostly doing all the research works with the bag of words like TDM, term documents matrix, TF, IDF, and then we actually apply some matrix decomposition, etc., to do that. So those actually comes under the syntactic curves. Then, currently, we are actually in the semantic curves. So where we actually try to represent the context of the text. Then the future, we believe we are getting inside the pragmatic curves. So based on the scenarios, how we can actually represent the text. So those will actually get inside the pragmatics. So now we actually detailed out what are the methods of text representation method we're going to see. So we are just we're going to start with the bag of words, term documents matrix representation, and then to solve certain problems in the term documents matrix, how the term documents and inverse document matrix evolved. Then in order to represent the word, how the term feature matrix is actually derived from these two matrices. Then in the distribution representation method, in order to represent the context further clear, how matrix decomposition like SVD or singular value decomposition or non-negative matrix factorization applied on top of these matrices to derive the context, or actually will be covered in this methods. Then getting inside the neural network, we'll be starting with the word to vec, glove, dog to vec, and deep learning. Okay. And in today's session, we'll be seeing up to word to vec. In the next week or in the future session, we'll actually cover up the glove, word to vec, then a bird burst embedding. So this we are going to see. So I'm just taking a break now. Do you have any questions? Okay, so shall I proceed?
Yes.
Yeah, thank you. So let's actually start with the bag of words. In simple terms, we already explained. So given the sentence, first we actually formulate a vocabulary. The vocabulary would be unique words in the entire corpus. So here my corpus contains only 2 sentences. Okay, so just we are actually formulating it. And then what we're actually doing is like we are going to count it, like how many times that specific term that is called word is actually like appeared in a specific sentence. And when we actually like filled out, the term document matrix is actually like formulated. Okay. But if you actually look into the problem of this specific matrix, it doesn't actually uh, like uh, it doesn't actually like counts how the words are actually like formulated. Okay. Then how the words are actually like ordered, and the syntax means like the structure of the sentence is also like missing. So due to this, when you actually like take any two sentences, complicated sentences, take a sentence, two sentences. Boy chases the cat chases the boy. See, even though the context differs, but when you're actually trying to represent these methods, right, both will be like seems to be the similar. Okay. So those are the disadvantage of this method. And further, if you actually like see it, if you take any big corpus, more than we are actually using a content word like Amrita or Sen, we tends to use the stop words majorly in the corpus like or, in, is, we. Okay. So these are not contributing much towards, or like it won't be actually carrying the much of the like context. It just like helps to build the context, but it is not carrying the much of the context. So uh, usually in this type of matrices, these stop words will get the more weightage, but this content words are actually like won't be like having the more weightage. It will having like less weightage. So when we do some specific task, it won't be like performing better. And further thing is, if you actually like see the dimension of the matrix. Yes, any questions? Anyone writes? Okay, I'm just continuing. So the further thing is like this matrix, the dimension is actually like, if you take for this specific example, it's 2 cross 5. That is actually two rows and 2 cross 6. Two rows and 6 words are there. When we actually like practically, when we actually develop a system using this method, when we have like millions of records, then consider about the number of words in the column. So the matrix itself is becoming the big. So like practically we cannot actually use it. So this is called curse of dimensionality. So these are the problems which actually like summarized. It doesn't include the text properties which we actually earlier described, and the context will be depends only on the n-gram features. When we say n-gram, no need to take. These are actually called unigrams. So like we are actually like taking only one words. We can take bigram, trigram for 4 grams or up to the n-grams, whichever we want. So that n-grams only will contain the context, no other things. Then the curse of dimensionality. As the number of documents increases, the dimension of the matrix actually it will actually like increase. So the computation is actually become complex and costly. Then it has the bias towards the more frequently occurring words, which are actually like basically stop words. So to avoid this, the further methods are actually like evolved. So the first one is actually like TF-IDF. So where it tries to address the giving a lower weight to the stop words. So how it actually like does is, the approach is actually like same. First, it formulate the metrics which we earlier constructed, like the same metrics which we'll actually like construct. Then after constructing it, what it does is like it just divides with the inverse of the document frequency. For example, if you actually take the words Amrita, it is actually like here in this example, it is available in only in the second sentence. So it's like considered as a unique word. And if you take the word in, it's actually there in both the sentences. So that words like common words like sen and in are actually like divided by 2. So that is actually 1 by 2, 1 into 1 by 2. So if you actually like see it now, the rarely occurring words, Amrita, are actually getting higher weightage, but the commonly occurring words across all the documents is getting the lower weightage. Okay. So further to explain, if you actually take one example, the movie is great. The movie is terrible. Okay. So when you want to do the sentiment classification, the terrible and the great. So those are the unique words will get the higher weightage. The movie is, since it's appearing in both the sentence, when you do the sentiment classification, those words, the movie is will actually get the lower weightage. So this helps in actually like doing a better classification. So these are the one examples. So in the term documents inverse document matrix, they try to solve the problem of giving a lower weightage to the frequently appearing words across all the documents. But the other problems, that is actually order of the word and the context of the word that is actually carries, and the grammatical structure, those are actually like not considered. And still the curse of dimensionality, that is actually like as the number of words increases, your matrix dimension also like will increases. So this problem still exists. So same I have been actually just like highlighted here. And further to just like to do the word representation, like they actually like went for actually like creating a co-allocation matrices. So here what we actually like do is both we terms are actually considered in the rows and columns, and we're just like calculating how closest they are actually like co-occurring with. Okay, so in the examples that we actually like seen, so if you take these examples, so how many times that Amrita and Amrita, two words are actually appearing two next to each other in a like immediate sequence. So there's nothing is actually like occurs. So we don't have that is zero. And same like we'll do for R, Sen, and etc. In Amrita. So this actually like is there. In Amrita is actually like there. So it will actually get the frequent of 1. So like that, we actually like formulate this entire matrix. So when we actually like do this, so how it will actually help us to uh, have a bit amount of context, because like we're actually like measuring the co-allocating words, but still the curse of dimensionality order of the word is actually like not maintained. Okay. So in order, if you want to increase the semantics, means instead of actually like looking into the word in a like immediate word, we can actually like include a further additional words. So suppose if you take the window of size 2, you can just look under the within the two words whether it is actually co-allocating with Amrita. And if you want to increase the context, you can increase the window size to the 4. So within the 4 words, that Amrita and Sense are actually co-occurring with each other or not. So that can be actually like calculated in this term feature matrix. So as we just like discussed, still it doesn't include the text properties mostly. The context will be like depends only on the co-occurrence windows that we are actually like selecting, and the cause of dimensionality exits. It's directly depends proportional to the number of words in the vocabulary, and it's actually like more frequently occurring words means like within a small corpus we can actually like build a better contextual matrix comparing the TDM term documents matrix or TF-IDF. Now, on the further to represent the more semantics, that is actually context. So what we're actually like doing is like people tries to explore or experimenting, applying matrix decomposition on this matrices. Okay, so just consider this matrices as matrix A. If you actually like see here, this is the matrix A. So when we are actually like trying to do want to find the similarity. So if you want to actually like when we actually like projecting that is matrix A to the matrix transpose of the same. So you're actually like measuring the similarity between the sentence 1 to the sentence 1, then sentence 1 to the sentence 2, and vice versa in the proxy manner, like sentence 2 to the sentence 1, sentence 2 to the sentence 2. So all the diagonal would be like self similarity. The other elements would be like cross similarity between the sentences. And this gives you the a bit context of like the sentence representation. And when we do the reverse, that is A transpose A, we are actually measuring the similarity between the words. So when you actually like take the here also diagonal, it would be like self similarity. And when we take the all other elements, would be like cross similarity between the words. So here it actually like adds a bit amount of context like within the words. So typically like in singular value decomposition and non-negative matrix factorization, these kind of methods are actually like applied to find the context or the representation for the document or the word. So which is basically embeddings. Okay. But if you actually like see it, it also like not like includes the text properties, but it actually like derives a bit amount of context. The curse of dimensionality still exists because like we're actually working on the matrix which we constructed earlier out of TDM or TF-IDF. So the curse of dimensionality is still there. Now to solve that only like the first embedding, it's called word embedding. So first embedding method's been actually like introduced, that is actually word to vec. So in the word to vec, we have like fundamentally we have two methods, that is continuous bag of words and skip graph. Okay. So here, given the how it actually like finds this, I have the detailed one in the hands-on, but I'm just like trying to give you the glimpse on it. Okay. So if you take the continuous bag of words, the word to vec, it basically like replicates the neural network principle. Okay. So here you can actually like have, you can see like we have one input layer and one hidden layer and one output layer. Okay. And the input layer, we are actually like feeding the words. So here actually like we have, we just consider we have the word one, word two, word three, and here we have the word four. Okay. So the skipgram is actually like given a context. Okay. So like you can just like consider cat sat on the mat. Okay. Or cat sat on mat. Okay. So given the context, cat sat on, the output you will be like predicting the mat. Okay. So when we actually like train this in actually like huge corpus, the intermediate learning that we are actually like doing, it actually like represent the context of the word. Okay. And the best part of this method is like the earlier methods, we no need to actually like feed the entire document in a one go. We actually like, as you know, the since you're already like done some experiments on the neural network, we know like when we train it, we pass only the batch, which means like a small amount of data only we are passing it to learn at the time. And in the next iteration, in the next batch, we are feeding further more examples. So like here also, like you can pass it by context so that the intermediate matrices actually like learns over the time with the less computation. Okay. So those are the advantage of it. So here, if you see, we are passing the context to find the a target word. So when we do that, these words are actually like relates with the target words. So this is how the context has been actually like built. So when we actually like do more the hands-on experiment, we'll actually get a clear picture on this. So this basically called skipgram models. Okay. And on opposite to that, we have the like continuous bag of words. And the continuous bag of words, sorry for the confusion. So this is the continuous bag of words. We feed the context to find the target words. And on the skipgram models, we'll fix the target words to find the context at the output. So this is basically a skipgram model. But the disadvantage of this specific method is like it can represent only the words. Okay, one word only it can actually like represent. It cannot actually like represent the sentence. Okay, in order to do this, find the representation for the sentence, what we have to do is like we have to find embeddings for each word. Either we have to like sum it up, or take the average, or the kind of mean pooling we have to do, or we can actually like apply the matrix factorization also. Like just we can actually like concatenate all these words, and when you actually like apply to find the rank one, we'll get a one representation for this sentence. Okay. But if we do the average of this method, consider the same example, like cat chases the boy chases the cat. So both will have the same representation. Okay. So here also the context is actually included. The word is actually like included, but the problem is the order of the word, and also like based on the place the word appears, the context will be like missing out. So these are the like cons in these methods. So the glove and the other things I'll be just like handling in the next week. Now we'll actually like move to the hands-on. So before hands-on, if you have any questions, please let me know. Shall we proceed to the hands-on? Shall we practice some examples?
Yes, please go on.
Yeah, thank you. So just like everyone can actually like parallelly like experiment. So in the links which actually like earlier given, here you can see like there's an open in collab link is there, and someone wants to actually do it in your computer laptop itself. You can actually like download this specific notebook and you can try it out. All the examples are actually given, and directly if you want to do it on the collab itself, you can open it here itself. So this representation method that we're actually like now actually like seeing that we're actually going to experiment here. But in order to give the better explanation, I'm going to take the sentiment analysis as the use case to explain it. So just like opened it and connecting to the CPU model. Since these are actually like conventional machine learning algorithms, so we don't need the GPU. We can directly do it with the CPU itself. So I'm directly connecting with the available node. Yeah, it is connected. Yeah. So here, what I'm going to do is like I'm going to take a few sentiment samples. That is actually like the movie was excellent, the film was excellent, the movie was terrible, a terrible movie. Okay. So if you see this example, I purposely taken it. So if you take the movie and the film as the synonyms, okay, so both are actually like synonym, and the sentiments are actually expressed using the excellent and the terrible. Okay. So we are going to evaluate this representation, that word embeddings, by measuring the similarity between the movie and the film, and the excellent and the terrible. Okay. So the good representation method should say the movie and the film. So these two words are actually like similar, and the excellent and terribles are actually like it's not dissimilar. It doesn't have any similarity. So any representation method should have it. So what we are going to do is like taking this specific sentence, we are going to represent them as an embedding, a vector will be having the dimension of D. Okay, so it depends upon the method we use, this dimension will change. Let's start doing it. So first we have the corpus. The movie was excellent, the film was excellent, the movie was terrible, and the terrible movie. So I'm just like marking with 1 for representing the positive label, marking with 0 for representing the negative label. Okay. So just like we build the corpus, the data is ready. So let's start with the term documents metrics. So here, the conceptually, what we do is like first we actually like formulate a vocabulary, and then we actually like count how many times the specific word is actually like there in this specific sentence. Okay. So to do that, I'm just like going to use a count vectorizer from scikit-learn library, and the NumPy and pandas for just like for the matrix computation and visualization for a data frame visualization purpose. I'm using the pandas library. So just like we are actually importing libraries. Since these are actually default one, I'm not installing it. We can directly use it. So the first step is like we're actually like initializing the class that is count vectorizer. Then we are actually like feeding the R corpus. So if you just like look into what is our corpus. So this list of sentences is our actually like corpus. So what it does is like it will actually like when we call fit, it will formulate the vocabulary, and then it calls the transform. The transform will actually like against that vocabulary, it will construct the matrix. Okay. So the TDM will have that specific matrix. And I'm just like trying to visualization purpose to show the vocabulary. I'm calculating the vocabulary and building that matrices to show you. And after building that matrix, what we're actually doing is like we're actually like finding the cosine similarity on this specific matrix, like doing the self similarity. And from that, we are actually measuring the similarity between the document 0 and document 1. So here the document 0 is a positive statement. A document 1 is also positive statement. The document 3 and document 4 are actually like negative statements are there. So what we're actually doing is like we're actually like showing the similarity between document 0 and document 1, that is actually like movie versus the film. And then the document 0 versus document 2, that is actually the excellent versus the terrible. Okay. So if you see now, this is the vocabulary which we actually like built. That is the unique words in our sentences. We have this, and we just like counting it. So we got this specific matrix. So if you want to do the document classification or any kind of sentence or paragraph level tasks, we can use the row. And if you want to do any word level tasks, like paraspeech tagging, feature extraction, or named entity feature extraction, if you want any word level tasks, we can take the column vectors. Okay. So if you actually like see it, the document 0 and document 1, both are actually having the percent similarity of 0.75. The same document 0, that is actually like a positive statement and the negative statement, both those also like having a similarity of 0.75. Because if you see the document 0, excellent, the movie was excellent. Okay, so if you see these are the statement. The document 1, the film was excellent. Okay, so if you see like the movie alone got 0 and film here it got 1. Okay, when you find the similarity, these are actually like you can see like 1 1 1 1 1 1. So like it's a kind of 3 by 4. So it's a 0.75 similarity. The same is actually like happened over here as well. So if you see like the terrible document 2, that is actually like the movie was terrible. So the terrible is getting like calculated here, and the document 0, if you see it, this alone goes. All others are actually like having the common words. So it is also getting the same similarity. So this method, as we earlier seen, it is not actually like useful at all, because like it doesn't contain the word order, or it doesn't contains the or considers the context of the word. Now also like we'll see the similarity between the specific words, that is actually like the similarity between the movie and the film. So here if you see, similarity is actually completely 0, which means the embeddings that you're actually like created for the movie and the film, it is not reflecting the context. It's just like reflecting the frequency alone. So that's why if you take the embedding, there is actually film, this row, this column, and the movie, this column. When we actually like finding the similarity, is becoming 0. Okay. Yeah. Any questions?
Nope.
Yeah. So now the next the term frequency, inverse document frequency, as we actually like seen earlier, nothing. On the same matrix, what we're actually like doing is like we're actually inversely applying the document. It actually like in document it is actually like appears. So if you see here, the words like the, was, and the movie. If you see, like, it is appearing at most like across all the documents, like most of the documents. So these are actually should get the lower weightage. The other things like the terrible and excellent should actually get more weightage. So that is the concept, the TF-IDF, which actually like takes. So to do that, again, for TF-IDF vectorizer, just like importing, then same principle, we're actually like doing the fit transform. Like fit will build the vocabulary, transform will represent the metrics. Then we're actually like visualizing how the matrix actually looks like. Now, if you actually like see this, these words, the and was, is actually like getting a lower weightage. But like the rare word means like less frequently appearing words like the excellent, the film, okay, the terrible, or you can see like these are actually getting more weightage. Okay, so means like the features which contributes towards doing the classification getting more weightage in the TF-IDF matrix. So the same similarity measure we will do it. So now if you see that the uh, similarity between two positive statements is 0.68. The similarity between the positive and the negative statements are actually like 66. It is actually a little bit reduced, but like it's not enough. Okay. And the same if you see the relation or the semantic similarity between the words, the synonym words like movie and the film, if you see, it is still 0 because it's not carrying the context of the word itself. So same, like it's a self-study notebook. Whenever you get a time, just like just like try to go with this readings as well. It gives you more information. So now we are actually getting into the word embeddings. Okay, so word embeddings is actually like it's actually like built based on the distribution hypothesis. That is that you should know a word by the company it keeps. From the proverb, like one can actually like judge the person by the friends they keep. Okay, so that's the some kind of a hypothesis. So here we have like two things, like that is actually like SIBO and skipgram. So SIBO, we already seen it. From the context, we're actually finding the target word. Okay, the man loves his son is the sentence. So given the words, the man, his son, we want to find the target word that is actually love. So when we're actually doing this, learning this process, the intermediate network will actually like learns the semantic representation for these words. Okay, just an opposite to that, skipgram is actually like given the target word, it will tries to map it to the context it carries. So just like both actually like reverse of each other. So this is the architecture of the skipgram, how it actually like learns. Just like nothing but this is actually like an or not encoded vector. So how it actually does is similar principle only. We have more detail in the below cells on we are just like computing it practically, but just like to give you the theoretical perspective. Uh, this would actually like have at most like all or actually like 0 would be like equivalent to the vocabulary that we're actually keeping. Vocabulary means in our corpus a number of unique words, and only one word would be like the target. So this is skipgram. So the target word alone will having the 1. Okay, and output nothing but you're actually like predicting the context it carries. Okay, so suppose like if you actually like see this allows actually like if you take this as the 5-word vocabulary, so it will be like I'll just like this example itself. I will just try to show. So on this specific example, if you take this example, like we have 1, 2, 3, 4, 5. 5 words are there. Just like taking 0th word, first word, second word, third word, and fourth word. So we'll be like just formulating a one out encoded vectors. So this is the first word. Okay. So this is the first word, which is basically the man loves his son. Okay. So this is actually like the so man would be 0, 1, 0, 0, 0. Louse would be 0, 0, 1, 0, 0. Okay. S would be 0, 0, 0, 1, 0. Sun would be 0, 0, 0, 0, 1. Okay. So this is just like an eigen, an I matrix only. Okay. So we see like when we want to find the word louse, this would be the input in the skipgram when we actually want to find the target word. So given the word love, we have to predict the context. The man, his son. Okay. So we'll just like formulating a pair. The pair of like louse is the input. The output you have to predict is the man, his son. So practically how we actually just like wants to find is, it would be like, this would be our input. The output would be like all together. When you just like sum it up, it will be equivalent. So like 1, 1, 0, 1, 1. So here we are actually learning a term like that is an x, which actually like when we actually like multiplying, it will actually find the target words. So this x is the embedding which we are actually like learning it. So same is actually like given here. All will be like zeros. The only target words would be like here in the skipgram model. Output would be like the target words of your interest. And here it will be like whatever we are learning is actually like called the embeddings. Okay. But the best thing is like, unlike that term documents matrix and inverse document matrix, that the dimension of the embeddings in our control. Okay. So it won't be depends on the vocabulary size. It depends on the size you are actually fixing. Typically, people tends to use between 300 to 500 is the embeddings size. So as you fix those many dimensions, you will be like having it. Okay. And the continuous behaviors is actually just an opposite to the skipgram. So where the input like you will be like having the context, the output you will have like target only one word. You will be like predicting target word of interest will be predicting. So here you can just like see some example like how we are actually formulating the input output pairs. So on the skipgram, the quick, the brown. So like in this specific sentence, the quick, the brown. The window size, we are actually taking it as 2. Okay, so it will look into the both left side and right side. In order to increase the more context, we can just like increase more window size. If you want 4, then it will be like 1, 2, 3, 4. Up to the jumps will come. So now we are taking only the window size of 2. So in the skipgram, the input, as you see, like one word is actually there. The output, the predicting context would be the quick brown. Given the word the, predict, quick, and brown. So that's how this input output formulated. The CBOW is just like opposite. The quick brown is the context input you are giving, and you are actually predicting the. Okay. And coming to the skipgram, again, for the next words of quick, the left side, the is there, right side, brown and fox are there. So given the word quick, we're actually predicting the brown fox. Okay. So when we doing this activity over the huge corpus, the intermediate, this specific weights are actually learns the context of this entire corpus. Okay. And this is actually like how a typical embedding space looks like. When we wants to visualize, we can visualize later, but we can just like here understand how the words are actually like closely appearing in the semantic space, like long, longer, longest, fast, faster, fastest, or like the relation between the king and the man, king versus the queen, queen and the woman. So this is how the context, the word embedding actually like learns. Okay. So let's just like do it. So I'm using GenSim library, which is typical, which is generally we will be using it for doing the word-to-vec tasks. Okay, it won't be default installed, so we're just like installing it. and I'm just calling it again, the specific APIs. Okay. So here, if you see, like, I'm not going to train it from the scratch. We are going to use one model, like which is already trained on the huge corpus and kept. So each corpus to learn the weights in this specific weights are actually already learned and kept, and we are going to use it only. So from this like specific moment only, the term pre-trained is actually got introduced from the word-to-word model only. So where we will be like already pre-trained model would be there. No need to actually like every time train it from the scratch. You can directly like use it. So it's having like around 1.5 GB of memory. It will take some time. So meanwhile, if you are actually like experimenting parallelly, if you have any queries, I will take.
So can I have a question? Can you hear me?
Yes, please. We can take the questions. Meanwhile, it's getting downloaded. Yeah.
Okay. So actually, I like simple and classic methods, but more and more since transformers have basically dominated the whole NLP plane, right? Usually, right now, almost nobody uses the classic word embeddings or even the TF-IDF or the simple bag of words models, language models. Do you yourself see any useful or like a good use case for those classic methods, even right now, even with the in the days of transformers and large language models?
Yes, Professor. So if I get your questions correct, that conventional method that is actually TDM and TF-IDF, do we use it in any use case? Is the question right?
Yes.
Yeah.
In present times, right? So is there a good use case for TF-IDF and skip grams and CBOW and things like that?
Yes, there are actually like many is actually like even now it's applied in specific industry use cases, Professor. So, for example, right, might be like you might actually like we might actually like seen right that the GitHub pull request raised like we used to raise it to merge it with our repos and etc. So like that in industries like they have called ticketing systems. Each industry or inside each company they have the ticketing systems to raise a request or raise any consent and etc. So those are actually like only closest that is actually closest to the specific industry. So when they are actually like not in the position having more data, or like when they are not in the position of like sending the data out, okay. So what they actually like tends to do is like still they are actually using typical methods on a small corpus to do the basic classification. So received a specific ticket like some XDG failure, getting help from some etc some confidential information, they will be like mentioning it. So in those cases, the transformer models or like this like our the recent embedding models. So those won't actually like know or have the knowledge of those words. So and those words are actually like limited only to the specific domain. Okay. So in that domain, they actually use a typical TDM or TF-IDF so that they can actually like easily process it. And it won't also like it's not computationally heavy for them as well. So wherever much context is not required, only to use for the a small classification, that is actually like more than enough.
Okay, thank you. And also, so thank you for reminding me. So like basically industry has a very sort of good, you know, scope of using, or like a way of using simple methods, right? So you not always need 100% or like 99% of accuracy. Sometimes it can be like 85%, for which the classic methods, or the the word embeddings are perfectly fine, right?
Yes, yes, absolutely, Professor. And also, like, in order to do the simple classification, they no need to actually spend much on the GPUs and the bigger things. So, like, a smaller machines actually like more than enough to do the day-to-day activities.
Okay, perfect. Thank you. And I think it already just finished, right?
Yeah. So the download is actually like completed. So now what we're actually going to do is like with this model, we're actually like take the specific words of an interest. Earlier which we actually tried with the TDM and TF-IDF, which actually like failed. Let's see how this performs. So we just like got the vectors. So if you see that the dimension is actually like 300. Okay. And these are the first 5 numerical values of that vector of this this vector, specific vector. And I'll just like show it. So there are actually like 300 values, sequence of numbers we can see. And it's first 5 dimension is actually like what we actually like just visualizing here for the movie and the film. Okay. So if you see it here as the number wise, this actually like looks very different. But when we actually like find the similarity now between these movies, now you can see like the similarity between the movie and the film is actually like 86. And the movie and the terrible is actually like 0.16, that is 16%. And the excellent and terrible is actually like 33%. So now using this, right, we can see like how good this representation method in learning. Okay. And how we can actually like now do the document level similarity. As we actually mentioned earlier, these word embedding models can actually like represent only a single word. It cannot actually represent the entire sentence by default. Okay. So that's why what we're actually going to do is we are actually going to do the averaging method. So what we're actually doing, all the words we are actually just taking as a vectors, and we are just like finding the average of it through the NP mean. Okay. So now if you actually like see it, the similarity. So what we actually like done is given the inputs and sentences. So in our corpus, again, I'm just like printing the corpus, what we're actually like doing it. So these are our 4 corpus. What we actually do is like we find the vector for the movie was excellent. So 4 vectors will come. And when we just pass it, you can see like model of word we are calling, all the 4 vectors will come, and we just like find the average of it. And once we get that average in the metrics, we're just like finding the cosine similarity. So this is actually like similarity matrix between the documents. So all the diagonal elements are actually like self similarity, that is actually between same itself. That is document 0 similarity is here. Document 1 similarity is here. Document 2 similarity is here itself. So all are 1. If you just do the other elements, it is the cross similarity. So document 0 and document 1, that is actually like positive statement is 95%. That is, if you see right here, the movie was excellent, the film was excellent. So the synonym of the movie and the film has been actually presented here. So still it is getting 95%. But coming to the document 2 and document 3, the movie was terrible, the terrible movie. So here you can see like as per the word changes, the similarity values are actually getting reduced. And coming to the negative statement, if you see like document 2 similarity is 1, that is same, like self similarity. And document 2, document 3 is actually 84. That is between this movie was terrible, terrible movie. Okay. So same, it's vice versa applicable. This is just a reflection matrix only. Okay. So now let's actually like do a little bit deeper insight like how these embeddings are actually like formulated. Okay. So what we are actually like doing in the next step is let's actually like using the gens in this library, you can directly train your own corpus. Suppose if you're using it for any of your research, like this GenSim library, you can directly use it to do it. But just to give the an explanation like how the things are actually working under the algorithm, and what I'm going to do is like I'm going to train this SIBO and the skipgram models for the our specific corpus. That is actually 4 sentences. So I'm using Torch to build the algorithm of word to vec. So corpus we are actually created. Now we are actually like formulating the word index mapping. So if you actually like see it here, the film is actually getting 0 index. Terrible is getting 1, excellent 2. Like 5 words are actually there in our vocabulary. Okay. And since only 5 words are there, what I'm going to do is like my embedding dimension, I'm fixing it to 2. So if you see it here, here it is actually like 300. The embedding dimension is 300. Since the corpus is big, since our corpus is actually very less, only like 5 words are there, I'm going to fix the embedding dimension as 2. Okay. So the scripts, we are going to first start with the skipgram. The skipgram is very simple. Given a context, so given a target word, we have to find the context. Okay, the movie was. Okay, so we are fixing the window size as 1. Just like nearby words alone, we are actually like saying it. So the first thing is like we're actually like formulating the pairs, the input output pairs. So you can see like given the word the, it has to find movie. Given the word movie, it has to find the movie was movie was excellent. Like that, the pairs would be like formulated. Okay. So if you see the entire skipgram data, you can actually see it here itself. So these are the pairs we have. The movie the, movie was movie was excellent. Excellent was the film the, like that, the pairs will be same. So these are the input and these are the output to be predicted. So the good part is like, if you see, right, it's actually trained in the neural network way. Given the word only once. So first it learns this, it will have a loss, then it will find further goes to the next. Like that it goes. Due to this only like this word becomes success because like we can actually feed as much amount of data we have. The billions of words also we can actually like feed it so that it will actually fit under the memory. So here I'm just like defining the skipgram model. It's simple. Like here we can see like first we're actually like fixing one matrix, which is our vocabulary size, unique words, that is in our case 5, and the embedding dimension, that is actually like 2. So in our case, we're first initializing a matrix that is actually like 5 cross 2. Then the output matrix, which would be like the opposite, the embedding dimension versus the vocabulary size, that is 2 cross 5. Okay. So in the earlier image, as we've seen here, right? So this is the one matrix, embedding matrix, and this is another matrix, the output matrix. So this is 5 cross 2, this is 2 cross 5. So we define the two matrix. So when we call the forward would be nothing. We just like passing the word index, that is 0, 1, 2, 3 as per the word. Okay. And the embedding it's getting right is again actually like multiplied with the linear layer, which we're actually like having it here. And finally, like we are taking the softmax to have like which words are actually having maximum probability. So this is the skipgram model. The continuous would be like a little bit different. So I'm just like showing here itself. It has both two matrices only, but what we're actually doing is like on the intermediate, we are doing the aggregated. Aggregated means input, we are actually like feeding 3 words or 2 words, right? So that we are actually just doing the summing it up. So here, coming to the skipgram back. So this is the algorithm or the logic we are defining. Embedding dimension as 2, number of epochs are 100, a learning rate, I'm just keeping very minimum, 0, 1. So we are starting with the vocabulary size, that is 5 in our case. Embedding dimension is 2. Loss function, normal loss assembly defining. and stochastic gradient descent only. We're fixing it optimizer. And as you see, like we are just like one by one, center comma context. Let me print this also so that it will be like helpful. So every I. Or maybe like one word. Just like put. Just like printing only one statement. Let's try this. So we have now actually like trained our epochs. So now we can actually like see that one embedding I'm just finding for the movie. Okay. Same, I'm just like doing for the SIBO. SIBO is just like opposite to that. The input we are actually feeding the output to the context. The output we are actually like finding the target word. Okay, so here since we're actually like doing it two, we just like here we're just like taking the sum of it. It will be like just equivalent. Equivalent means like how it actually behaves is just nothing. Because suppose like the word B having the first index out of 5. Okay, so when we just like add this with another word that is was, it will do nothing but sorry. Okay, so it is actually like considered as a plus. So when we actually just like sum it up as a numpy, so it will be like it's a kind of sum of this only. Like that's why like this aggregation layer actually like behaves. So let's go through the SIBO. So SIBO was, as we see, like the opposite. We are following the pairs context. D was find the movie. Movie excellent context, find the word was, and the was, find the target word film. And same, only we're defining. The only thing is like the intermediate aggregation, we are actually doing it to combine the words, context words. So the same principle we are doing it here. So now we can see like this is the embedding. We are actually getting it for a small data, that is 4 sentence. Now let's actually like compute the similarity between the movie versus film. Movie was terrible, excellent was terrible for the corpus that we actually like built. So now we can see like for the movie versus film, the skiggram gives the 97, but the SIBO is actually giving less. The movie was terrible. The skiggram is 99. The SIBO is actually like 95. Excellent was terrible. Skiggram is minus 13, but SIBO is actually like 79. Okay. So what does it shows like how we can actually like train this. So when we actually like having more data, this similarity is actually like will actually like get better. Okay. So and as per the initialization of the epoch also will affect. Actually, earlier when I actually like done this experiment, it was actually like at most actually reflecting how it is actually like having it. But now the initial seed is actually getting might be like set differently. Okay. So you can just like do the multiple iteration. Might be at one specific seed, we'll get the best value. But when we have like large data, this similarity would be like would result in a better one. Okay, so different value we're getting. So in order to avoid that, we can just like set the random seed value at the top so that this deterministic output, we can always get it. Okay. So the final conclusion is like, as we actually like seen, like in the overall thing, the traditional methods, the term documents metrics, term document, inverse document frequency matrices are actually like not good for defining the context and etc. It is only will be like helpful when we have having less amount of the data and would be like very rare data. Okay, if it required, we can actually still use it. But this word-to-vec, these are actually like a pre-trained one. When we actually have the large corpus, when we actually like once we pre-trained, we can use the model again and again. No need to like train it every time. And further thing is like this word-to-vec still have the limitation of like representing only the words level. It cannot represent the sequence level, that is like sentence or the document and etc. That's why we need further representation methods. And also like this word-to-vec can't handle the vocabulary. Okay. For example, right, on this specific samples, we are just like finding the vector for word film, but I'm trying to do it for filmed. Okay. So when you do this, it will actually throw error because this is called like out of vocabulary, OOV. So it can actually only represent for the words which is actually like seen. Okay. To avoid that, we can actually do the subword mapping and etc. So those are the those would be like I would like to cover it in the next session. Like glove and fast text and bird would be like covered in the next sessions. So, and if you have any questions, please let me know. Also, like I don't want to actually take much time. That's why I just like a little bit rushed. Like whenever you have got time, please do this experiment and just like go through these materials. If you have any doubts, I can just like clarify you on one-to-one call or like in the next session also I can clarify you. Thank you, everyone. Yeah.
Thank you. Thank you. That was a full lecture about word embeddings. Thank you.
Yes, Professor. Thank you, Professor. So as mentioned, like the next session, I'm not sure like when and all are whether available due to the summer vacation. One more week, I would prefer to have the session on word embeddings.